Well, hello guys, and today we're going to answer question 8 from this consolidation material. This one is for the grade 12. Question 8 says a diver of mass 80 kilograms steps off a diving board at point A, 4,0 meters above the level of the water of a swimming pool. Diver enters the water at point B and comes to rest at point C. So, there are some important facts here. At point C, the diver is at rest. In other words, the speed here is equal to 0 at that specific point. That's an important fact. While the diver falls through the air, an average frictional force of magnitude 172 acts on the diver. So, from A to B, the frictional force is equal to 172 Newton. And let's take this one and move it here because maybe we can work here on this specific side. Act on the diver. The total work done on the diver by the non-conservative force while he moved from A to C is negative 6,240 joules. So the work done by the non-conservative force from A to C, work done, let's write it here, work done by the non-conservative force is equal to negative 6,240 joules. Okay, and that is the picture here. You have also that the initial speed of the diver is equal to 0. Alright, so this is what we have. Question 8.1 state the work energy theorem in words. And here, the net work done on an object is equal to the change in the object kinetic energy. They are two marks. This definition is in the summary of this specific material at the beginning of it. In simple, the work energy theorem, or the change in you can write that the net work is equal to the change in kinetic energy. There we go. Now question 8.2, use the work energy theorem to calculate the speed of the diver at point B. So we have to use the work energy theorem to calculate the speed at point B. So let's see, maybe we can use this side to work. Question 8.2. First of all, let's analyze what forces are acting on the boy as it's falling from A to B. We have two forces only. There is weight of gravitational force pointing down, okay, and there is the frictional force of the air pointing up. Those are the two forces acting on this specific dive. That is important. The displacement is straight down. Okay, so this one we need it because we need the angle. So now we're starting with the work energy theorem. We know that the net work is equal to the change in kinetic energy. You always begin from there. What is net work? Is the addition of the work done by all the forces. In this case, we have work done by friction, plus we have the work done by the gravitational force, and this is equal to change in kinetic energy will be half mass final speed square minus half mass initial speed square. Let me see if I can move it a little bit there. Initial speed square. Okay, we know that the initial speed is 0, therefore we already can say this one is going to be 0 because the diver moved from 0. Okay, now if we substitute here, we have two options. We can calculate each force separated, or we can substitute in the same formula. It's entirely up to you, but they are not difficult, so we can substitute it here. The work done by friction will be the product of frictional force. Let's write just a small f, just one f, friction multiplied by the displacement multiplied by the cosine of 180 degrees plus the work done by gravitational force is gravitational force displacement cosine of 0 degree is equal to half mass final speed squared. That is what we have. But the gravitational force can be broken furthermore. This one can be mg. Remember, you don't have to do this one. If you want, you can work separated. But in this specific equation is simple, so we can substitute it here. We have friction. And we can already okay, let's keep it friction. Displacement cosine of 180 degree plus mg displacement cosine of 0 degree is equal to half mass final speed square. Alright, we are there. And now we can substitute all the numerical value because we have actually everything. And then we get that the speed of this diver at point B is going to be equal to 7,82 meters per second. This is the answer here. Speed of the diver at point B. Okay? Now, the marks allocation here are as following. One for starting with the work energy theorem. One for the whole substitution on the left hand side. One for the substitution on the right hand side. There we go. And one for the final answer. There is only 4 marks for this question. Question 8.3. Is the mechanical energy of the diver conserved? Choose from yes or no and give a reason for your answer. Quite simple. The answer is no. Why is not conserved? Well, we can say because the net work by the non-conservative force is not zero, or we can say because of the system is not isolated. So let's write that one. Using energy principles only, calculate the distance from B to C. They want us to use energy principles. Therefore, we can use the law of conservation of energy. The work done by the non-conservative forces is equal to change in kinetic energy plus change in potential energy. Okay, we can begin from the, and we can break this one even more. We can move this one more to the left. There's enough space for this one. We can say that the work done by the non-conservative forces is equal to half mass final speed square minus half mass initial speed square. This one is the change in kinetic energy plus mass acceleration due to gravity final height minus mass acceleration due to gravity initial height. Now this one seems simple, but there is kind of tricks in here. We're going to see what we have and we're going to go further on, okay? Because in this case, when the diver is at point B, if we take B as a reference point, we have that one height is h, that is the initial height, but the final height from there, or distance, is going to be actually d. Alright, so we must take that one into consideration. This one is the 0 point. So we come in here, and I want you to see what I'm saying. Work done by the non-conservative forces is equal to half mass final speed square minus half mass initial speed square plus mass acceleration due to gravity final height, that is d, but d is negative because it's on the below point, so minus d. If I take this one, and this one is have nothing to do with direction, all right? If I take this one as 0 point, positive is up and negative is down, like the axis in mathematics, guys. So the distance down is negative distance. So that is what is going to happen here, minus mass acceleration due to gravity h. And now we can substitute the values because we have everything. I hope you understand this side here could be a little bit tricky. So now the values, we have all the values, so let's substitute everything we have here. Also note the following here. the starting point, if we take starting and finish from A to C, because that is the work done by the non-conservative forces, we cannot separate this one by part. So the initial velocity at A is 0, as well as the final velocity at C is also 0, as you can see there. That is why it's 0 here on both cases. Okay? D is equal to 3,96 meters. There we go. And if we give marks to this final question, this one by starting with the energy principle, which is the law of conservation of energy, one by the substitution of the work done by the non-conservative force, one by the substitution on this specific side, all this one, because this one is 0, is also part of the substitution but doesn't even need to be there. And then one for the final answer is only 4 marks for this one. The marks here are a little bit stingy. Guys, this is all for this amazing difficult question to solve. Thank you for watching. I hope it helped. If it helped, thumb up, subscribe for the channel, share, write comments, and I'll see you next time. Mr. G